คือเราจะมาเน้นในของซอฟต์แวร์ Abacus นะครับซึ่งซอฟต์แวร์ Abacus เนี่ยทาง GISDA เนี่ยใช้เป็นหลักเลยใช้เป็นหลักอะไรใช้เป็นหลักในการดีไซน์นะครับstructure โครงสร้างครับของอากาศยานและดาวเทียมนะครับซึ่งตัวเนี้ยเพราะอะไรเพราะส่วนมากเนี่ยอย่างที่เรียนไปอากาศยานและดาวเทียมเนี่ยจะเป็น structure ที่ทำมาจากคอมโพสิตวัสดุคอมโพสิตและ Abacus เนี่ยมีฟีเจอร์ฟังก์ชันนะครับที่เป็นที่ใช้ง่ายที่เป็นวัสดุคอมโพสิตที่ใช้ออกแบบ orientation direction ทิศทางทุกๆอย่างlayer pie นะครับไม่ว่าจะเป็นการดู result ค่าเทสไซฮิลฟีเจอร์ตัวนี้จะใช้ง่ายนะครับการฟิลแบบ parameter binary condition นะครับการทำ topology design ทุกๆอย่างพวกนี้ตัวนี้จะใช้ง่ายมากตั้งแต่ที่ในทีมนะครับทีม R&D ที่ใช้มานะครับซึ่งคิต้าทำอะไรไปบ้างใช้ Abacus ในการทำโปรเจกต์อะไรไปบ้างนะครับอย่างเช่นGISDA เนี่ยก็มีการในการใช้ในการออกแบบเกี่ยวโดยหลักๆเลยเนี่ยที่ออกมาเป็นโปรดักต์ของเราได้เนี่ยก็คือเป็น wingbox ที่เป็นคาร์บอนไฟเบอร์เรียว 100% และสามารถรับแรงใช้งานได้จริงนะครับแล้วมีผลค่าความแม่นยำเนี่ยของระหว่างการทดสอบแล้วก็การ FAE เนี่ยไม่เกิน 10% นะครับซึ่งถือว่าน้อยมากในระดับ component testing นะครับทีนี้สิ่งที่ผมจะมาพูดก็คืออันนี้ขอเป็นภาพรวมก่อนละกันว่าGISDAเนี่ยโปรเจกต์เนี้ยGISDAเนี่ยร่วมทำกับบริษัทอะไรบ้างนะครับตัวนี้เราก็จะมีที่ร่วมทำก็จะมีมหาวิทยาลัยมอบูรพานะครับทำกับดร.ลอเรนซ์แล้วก็บริษัท Aerowork นะครับโดยบริษัท Aerowork เนี่ยจะสนับสนุนเราทางด้านการผลิตนะครับ manufacturing แล้วก็ทางดร.ลอเรนซ์มิกกับผมจากทางGISDAเนี่ยโมบูGISDAเนี่ยจะร่วมในเรื่องของการเทคนิคในการออกแบบและการทดสอบนะครับซึ่งตัวนี้เราก็จะมีการทดสอบไล่มาอย่างที่เห็นนะครับก็คือเราจะมีการทดสอบตั้งแต่ full bond test element test component test level และ full scale ซึ่งพวกนี้ในการทดสอบเนี่ยเราจะใช้ facility ของ GISDA ทั้งหมดเลยในห้องปฏิบัติการ Galaxy หมดเลยซึ่งเริ่มแรกเนี่ยเราก็จะต้องหา material property ตัวนี้เราต้องหา material property ตัวนี้ครับเข้าไปเพื่อจะเอาไปใส่ในซอฟต์แวร์ Abacus นะครับเริ่มแรกเนี่ยเราต้องทำการเทสก่อนนะครับสิ่งที่เราเทสก็จะมีการเทส tensile compression impingement แล้วก็ fractional strength เนี่ยพวกนี้พอเราได้ค่า property นะครับของ carbon fiber วัสดุ carbon fiber มาเนี่ยเราก็จะเอาไปใส่ในซอฟต์แวร์ Abacus ที่ในฟีเจอร์ที่เราเรียกว่า material property นะครับพอเราได้ material property แล้วเนี่ยเราก็จะมีการออกแบบนะครับโดยใช้ CAD นะครับ computer design นะครับในการมาออกแบบริบนะครับในระดับ component element level ก่อนที่จะไปประกอบเป็น wingbox นะครับออกแบบเราใช้อะไรโดยเราใช้วิธีการทำ FEA อย่างภาพแรกเราจะเห็นว่าเป็นริบของตัว spoiler นะครับและตัวล่างเป็นริบที่เป็นคอมโพสิตที่เราพัฒนาขึ้นมานะครับเราก็เริ่มจากการทำเล็กๆก่อนเราก็มีการ manufacturing นะครับแล้วก็เอาที่เราออกแบบจากซอฟต์แวร์ Abacus เนี่ยมาทดสอบมาผลิตแล้วก็มาทดสอบนะครับแล้วก็เทียบค่านะครับพอเทียบค่าเนี่ยเราก็จะดูว่าค่าที่เรารันนะครับออกมาจากซอฟต์แวร์แล้วเนี่ยกับค่าที่เราทดสอบเนี่ยมันเกิด error กันเท่าไหร่ซึ่ง2โปรเจกต์เนี้ยจำได้ว่าในระดับ element test เนี่ยคือไม่เกิน 5% นะครับที่เราได้ออกมาเพราะฉะนั้นตรงนี้มันเป็นค่าreference ที่ยอมรับได้เราก็เลยเอาไปพัฒนาต่อนะครับเอาส่วนพวกนี้ไปพัฒนาต่อออกมาเป็น wingbox นะครับที่เป็น wingbox ของในระดับที่เป็นปล่องเครื่องบินที่เป็นส่วนหนึ่งของปีกเครื่องบินเนี่ยโดยใช้วัสดุคอมโพสิตโดยใช้คาร์บอนไฟเบอร์เพียว 100% ทั้งหมดนะครับแล้วใช้ Abacus เนี่ยออกแบบการเสริมแรงนะครับว่าจะต้องใช้กี่พายนะครับใช้ direction ไปทางไหน orientation เป็นยังไงนะครับ stacking sequence เป็นยังไงซึ่ง Abacus ตัวเนี้ยสามารถใช้ในการออกแบบได้หมดเลยนะครับนี่ครับก็คือ หน้าตาฟีเจอร์ของ Abacus นะครับที่เราใช้ในการออกแบบนะครับนะครับแล้วก็อันนี้ก็คือการออกแบบดีไซน์ของในเรื่องของ stacking sequence นะครับAbacus ตัวนี้ก็มีนะครับในเรื่องของ layup นะครับแล้วก็ใส่ material property สุดท้ายเนี่ยพอเราใช้ Abacus ออกแบบ wingbox composite wingbox ทุกอย่างมาทั้งหมดแล้วเนี่ยเราก็ต้องมีการทดสอบนะครับในระดับ component test เพื่อจะเปรียบเทียบค่าให้ได้ว่าwingbox เนี่ยตัวเนี้ยที่เราทดสอบที่เราดีไซน์มาเนี่ยในแต่ละจุดเนี่ยอย่างไม่ว่าจะใช้ strain gauge ก็ดีจะใช้load cell ก็ดี displacement ก็ดีเนี่ยในจุดที่เราสนใจนั้นๆเนี่ยอย่างเช่นมีจุด peak load เกิดขึ้นบน surface ของ carbon fiber ผมตัวแต่จุดนี้ก็เอา strain gauge ไปแปะแล้วก็ทำการทดสอบใน condition เดียวกับใน Abacus ที่เรารันมาแล้วก็เทียบค่ากันซึ่งผลออกมาไม่เกิน 10% ถือว่าเยี่ยมมากนะครับตรงนี้นะครับเราก็ได้โปรโตไทป์นะครับจิสตาก็จะได้โปรโตไทป์ที่นี่ครับนี่ก็คือรูปที่เราเอามารันใน Abacus กับรูปที่เราทดสอบจริงนะครับนะครับตัวนี้นะครับแล้วก็จิสตาก็ได้โปรโตไทป์ที่เป็น wingbox ที่เป็นคาร์บอนไฟเบอร์เพียว 100% ที่มีน้ำหนักเบาและมีความแข็งแรงเท่ากับแมทริกครับผมครับก็ในส่วนของจิสตาก็จะหมดเพียงเท่านี้นะครับก็เดี๋ยวถ้าเป็นในรายละเอียดลึกๆในเชิงเทคนิคนะครับเดี๋ยวขอส่งnext station ให้กับคุณลอเรนซ์นะครับที่เป็นหนึ่งในนักวิจัยที่ร่วมนะครับในการพัฒนาคาร์บอนไฟเบอร์วิงบ็อกตัวนี้นะครับกับจิสตานะครับซึ่งเป็นนักวิจัยเป็นอาจารย์นะครับของมหาวิทยาลัยบูรพานะครับเดี๋ยวให้ดร. ลอเรนซ์อธิบายในเชิงลึกให้ฟังนะครับผมขอบคุณมากครับ
So good morning everyone and thanks to join this seminar today. So you can call me Lauren. I'm adjunct at Budapest University in material engineering and my specialty is composite design and simulation mainly for aerospace. So before starting, I will just introduce you very basically and from industrial point of view what is the simulation and what is the advantage of the simulation. So finite element analysis, FEA, is a process of simulating the behavior of part or assembly. So it can be one part of an assembly of different parts under different conditions, so different loading, using FEM, so finite element methods. So it can be mechanical, in mechanical engineering, electrical engineering, thermal engineering. We can combine also these different type of solicitation. But today I will just talk about mechanical design, mechanical numerical simulation. So what is the advantage of the simulation, numerical simulation? So if we summarize the design process, if we don't use simulation, we start by the concept, the design, the concept of your product, then you design, and then you need to validate your design. And it can be very long to validate in terms of time and cost. And when you are happy with your design, you can produce. If you use a simulation, the design, you use FEA to design and optimize your product. So you can save time on your validation because you have the step before, it means the FEA, you can already optimize your part. And if I zoom in the design and FEA step, I summarize the FEA by creating the CAD, so the 3D part, model construction. So as you can see, it's a big part, it's a big step, and then optimization. And what I want to say today is in FEA, the most difficult is to build your model, to construct, create your model. Optimization is fast. in terms of time, the model construction is the most important, this part for the FEA. If you have mistake in this part, in this step, you cannot optimize, you cannot trust your model. So the construction of your simulation, your model, is the most important part of the simulation. So in conclusion, FEA saves time and money. So many companies in Thailand ask me what is required, what is needed to use simulation. So what is the input? What are the inputs of FEA? So the first input is the geometry. So this is the 3D part. It can be IGS or STP in term of format. So you can use Kacha. Kacha is very good. It's one of the best software for CAD. But it can be another one. There's no problem. You just need to be able to save in IGS and STP format. Then you need all the force, so the loading, in terms of magnitude and location, where you apply, how many, and what is the magnitude, so the Newton, the load you apply, and the fixed condition. So it should be boundary condition to be more accurate. For this presentation, I use fixed condition. So where you fix your part, where you fix your geometry. So by example, for this geometry, we fix the bolt, the hole of the bolt. In terms of input, we need the mechanical property of the materials you use. So in industry, we use elastic property. So we need Young modulus, Poisson ratio of shear modulus, can be one of these two property. Yield strength for metallic and polymers, failure strength for ceramic because it's brittle, and for composite we need more property because we have the fiber direction. Properties, so same. Many companies ask me where I can find the property. The first is the manufacturer, the provider. So by example, here you have the data sheet of Torre for this carbon composite. So they give you the tensile strength, modulus, compressive. So they give you already some property, and they give you the standard they use to measure, to perform the experiment. But if you don't have the data sheet, you can find in the literature, in Google, something close to your property. But if you want really to have your property on your material, on your product, on the material you use, you have to do a mechanical test. So as Mr. Kittigan present, GISTA through Galaxy has the capability to perform ASTM test, both composite and metallic. Under NatCap standard, this is one of the top standards in the world. So you have to produce your coupon. Coupon is this, is a small specimen like this, following the standard, and you apply the solicitation you need, and you measure your property. What we need the design allowable. So this it's come from you, from the industry. So by example, it can be the maximum displacement you agree to have, the maximum stress, the safety factor you apply, etc. And for optimization, so what is the most important is industrial constraint. Optimization must be performed in accordance with the company, because we can do what we want in FEA. We can do everything. There is no limits. there is no physical limits. It's numerical. But the product, the part you produce, you have some constraint. Thickness constraint, material available you have, manufacturing constraint, etc. So to optimize, we must know what the company or the industry can produce. We cannot optimize without the company feedback. So this is very important, the relation company, industry, and the person or the, for example, G-Star, who performs the FEA. So I will make a small presentation in sandwich structure. It's a simulation we perform in Thailand. So first, what is a sandwich structure? So sandwich structure, it's a composite component. You have a thick core material here, and you have what we call skin or face sheet, bonded by epoxy adhesive, mainly epoxy in aerospace, bonded with adhesive film to the core. So we have a part like this. You can see on this picture, the core here and the skin in black. And what is the advantage? In fact, sandwich structure, you can compare this to the high beam used in the construction. This is the same thing, exactly the same idea. It's light and high stiffness. This is the same idea. The core of the sandwich is the web of the beam, and the skin of the composite of the sandwich is the flange of the beam. This is the same thing. So very light with a high stiffness. It is used in many applications. Aerospace, by example, in flaps, by example, some door, holds fuselage, not fuselage, wing part, nacelle, by example. Naval construction, you have also for the furniture, in the part inside the boat. Truck, lot of truck or bus, or the subway. I'm sure the subway in Bangkok use sandwich structure. And sport industry also, by example, the surfboard are made by sandwich structure. So sandwich are used in many applications. The skin need to be light and with a high strength. So mainly we use carbon and glass fiber and aluminum or aluminum sheet. So composite, carbon, glass fiber, or metallic sheet. Before moving on the next slide, on the next part, I would like just to give you some definition on the fiber reinforced polymer, so composite. So in composite, when we talk about composite, and especially for fiber reinforced polymer, we talk about fiber mixed with a polymer, or we call matrix. So this is a fiber reinforced by a polymer or matrix. And what is important in composite is you cannot use the fiber like this to design your part. So we use what we call the ply. So the ply is a combination of fiber, you see, many fiber with the polymer, with the matrix. So, sorry. So the ply is a basic element to design the composite. One ply, you cannot use just one ply when you design your part for the car, the fuselage. You need to combine the ply, and this is what we call the laminate. So laminate is a combination of ply, and each ply with a different fiber orientation to optimize. So we have, I will summarize. Sorry, I will summarize here. So if we start by the structure, by example here the fuselage, the wing, sorry, macroscopic scale. So this is a very large part. This is made by laminate. Laminate is a combination of ply, and ply is made by many fiber with epoxy. And this is a microscopic scale. So you can understand it's very difficult to optimize because you have a lot of parameters. So optimization of composite is not easy, and you have a large number of parameters. You can change the number of ply, the orientation of ply, the stacking, the size. So FEA, so you understand that FEA is a very good tool to optimize composite, and I will show you. So come back to the sandwich. We have the core. So the core is low density, very light, cheap, easy to machine to give the shape, and good formability to bend to give the complex shape to the part. Core material, you have most of the time you have two types of core: honeycomb, aramid, it's Nomex, it's Kevlar, or aluminium. So you can see here a picture of Nomex honeycomb, and you have different type of form: polyurethane, polystyrene, PVC, PET. You have a lot of type of form to use as core. So sandwich, when you want to design a sandwich, when you want to optimize, you have the core material, its density, the thickness. You can change the skin, you can change the material, the thickness, the layup, so for composite. So you have many parameters to investigate. And if you want to do this experimentally, if you want to produce and test, it's very expensive and you need a lot of time. So it's not for industry and company point of view, it's not possible, it's too expensive. So that's why we use FEA to simulate the sandwich. So as you can see here, we have the simulation here of sandwich, the core in green, upper skin, lower skin, so in gray, and you have the picture here of the test we perform and the simulation relate. So this is a bending, 3-point bending of a sandwich beam. 3-point bending, so we have the force on the top and lower support. And as you can see, the core, so the core is the green part. It uses 3D elements, it's a volume, and we don't simulate, we don't design the honeycomb. We don't design the shape of the cell. So you see, we don't do this. It's just a volume. And the property of the honeycomb is used to this volume, to the green part. So there is no need to design the honeycomb with all this detail. It's too expensive, too slow. You don't need. And using these methods, we can simulate a complex test on complex sandwich. So by example, here it was performed at GSA. So sandwich panel, carbon skin Nomex honeycomb. We impact, so we damage the sandwich.
จะมิวไอเรื่องงานโมบูอ่ะยังอยู่ที่มิวปะ
We inside the sandwich here we have a reinforcement inside, so you cannot see here, but inside we have a coating. It's a epoxy resin here to reinforce, and you have the picture of the simulation. So we can simulate, you see honeycomb here in gray, and the red part is the reinforcement. So we can simulate complex part with many materials using FEA. If I show you in an Abacus interface, so this is, by example, the volume of the core. You see the sandwich. We have here the definition of the core, lower skin, upper skin. And if I open, I don't have Abacus, so I have a print screen for you. So if I double click on core, in fact, you have the definition of the core. So we can see we have the form. And if I double click on the form, we have the mechanical property of the form. So the mechanical property related to the form is injected in the core material. And same for the skin. If I double click on Abacus interface, you obtain this screen, and we have the definition of the composite. You see, 1, 2, 3 ply. Each ply is a carbon woven. So we can change this. The thickness of the ply is 0.25, and each ply has one different orientation: 45 degrees, 0 degree, 45 degrees. And if I double click on the material, you can see the property input. So this is the data. So Young modulus, Poisson ratio, shear modulus. So this is typically Abacus interface. So it's very easy to implement this in FEA. And this property come from experiment and datasheet from the provider. So it's very easy in FEA to change any parameter. We can change the thickness, we can change the angle, we can change the property, we can combine different material. So you can understand that FEA, in fact, is very useful to optimize your part. So you save time, you save money. And now I would like to jump on the next presentation. So on the real application for the high altitude pseudo satellite apps, and we design and optimize the wind structure we call wingbox at G-Star. So drone are used in many applications. I will go very fast. Agriculture, forest observation, security, urban development, military application, etc., etc. And if we look the different type of UAV, you have different type of UAV and aircraft in function of the altitude. And today we talk about apps. So you see on the top right corner, and you see the altitude, 20 kilometer flight altitude. So this type of drone flies in the stratosphere. So it's a very high altitude satellite drone. This type of drone can fly during many weeks, almost 1 month. It is used for observation and communication application. So to fly during 1 month, the only energy you have is the solar energy. So you use solar panels. So the span length of the drone, of the apps, is very high, is very big, very large, about 25 meters. So it's a very large drone. And you understand that you need to optimize the mass. Mass is the key of the drone. You save mass, you save energy, so you have more endurance. And this is a picture of the drone from Airbus. So you can see the shape. It's a very light structure. And we try at G-Star to design a drone, this type of drone. So Mr. Kitty Kittigon already present this type of block approach used in aerospace. We have on the bottom the coupon. Then it's more and more complex, and at the end you have the drone. The objective of the project was to design and optimize aerospace product and to perform the mechanical test of this structure. So we want at GSTA to be able this type of test, which means on the top of the building block approach. So it means complex design, complex test. And to perform this, we carry out project on UAV apps, design and optimization of the composite wingbox. We produce the prototype with AeroWork company at Sriracha, Namchabang. We perform the mechanical test and we validate the test by numerical simulation. So some definition before start. A typical wing structure. So we have a beam, the beam inside along the wing are called spar. The part perpendicular to the spar along all the wing is called the rib. So I will talk about spar and rib. So spar is along the wing, rib is perpendicular to the spar. So first, we design and optimize the wingbox. We following the aerospace rules. Then we manufacture the prototype. Then we perform the test. And finally, we perform the simulation and we compare the simulation to the test. So design, manufacturing, testing, and finally, we compare testing and simulation. Sorry, okay, it's good. So design and optimization work package, the first step. So firstly, we obtain all the load, the force applied to the wing. Then we simulate the full wing, so the 12-meter wing. Then we calculate the force inside the wing. We create the CAD with using CATIA. Then we create the model, the detailed model. And finally, we optimize, so we reduce the mass. So load assumption, it was before the project at GSTA. We use a CFD application to simulate the wing and to obtain the aerodynamic force. I will not present this today. So the load was obtained before the project. Then we want to obtain the force inside the wing, and we perform a first optimization. So we design under CATIA the wing, 12.5 meters. You see the full wing. Very basic geometry, very basic approach. We apply the force we calculate before, and we optimize the thickness of the wing. You see, the color is related to the thickness. The first optimization of the thickness. So we reduce the thickness of the wing where we can until we reach our objective, just to have a first very quick approach. Using this, we calculate from FEA all the force between the rib. So this is the rib here, you see, in black. All the force between the rib and the structure. And using the force, we can design the rib. So the shape of the flange of the rib, you see? And using this, we can create the CAD. We use Catcha V5 at GISA. Then we have the simulation, the model of the wingbox. So first, very basic geometry. Always start by the easiest approach because it's fast and you can avoid mistakes. So you save time. So very basic first. No detail, no geometry detail. Very basic shape. Static analysis. We very roughly optimize the structure, and then we create the detail. So as you can see here, we have all the shape, all the part. So the spar here, you see spar, 1 spar, 2 spar in a range, and we have different rib, and you see the shape. Now we use the detail shape, and we optimize. We use the rules of aerospace. We use the failure. We use the yield criteria and the strain. So this is a allowable. I talked before. We use here, and we optimize the structure. So I will just give you one example. So for one rib. So by example, this part, the rib. By simulation, we can observe this area can be optimized. So here, the values are very low, so we can reduce the mass. So the part is too heavy. And what we did, sorry. So in fact, all this area, we can reduce the thickness. And what we did is we allow the structure, we create hole to save mass. So we save 40% of mass between the first design and the last. So you see, we save 40% of mass. And when we are happy, we manufacture the part. Then when everything was done, we manufacture the wingbox. So as you can see, we have the full structure with the optimization. So you see the hole in the part. So we save mass, a lot of mass. And next, we test the part. So as Mr. Kittigan present, we do a bending test on the wingbox. So we apply the force at the end. We have the load cell. So we measure the force and displacement. So the objective is to validate the complex, to perform the test and to validate by simulation. So how the simulation can help for experiment? FEA can be used for experimental approach. For one, to design the bench. So before doing the test, you can check the bench you use. And two, if you can simulate the test, if you can simulate the experiment, you don't need the experiment at the end. So or you can reduce the number of tests. If you can simulate the test, if you are able to perform the test by numerical simulation, you can reduce the number of tests. So we simulate the full test structure, so the bench and the wingbox. So you see we have everything. We simulate the bolt, the blind bolt we use. So you see we have the steel blind bolt. We apply the load here. No, we apply displacement and we measure the force in the simulation, sorry, as the experiment. And the first thing we did is, we want to be able to design and validate the test bench. We want to simulate the complex mechanical test. And thanks to the simulation, we can reduce the test number. So we simulate everything. So in the block approach, we are at this level, on the top level of the in the term of complexity. And for the first objective, before producing the bench, so before testing, we check by simulation the stress in the bolt. So we check the bolt and we check if we have failure. And in this simulation, we show we didn't have failure. So no failure in the bolt. We are confident we can test the wingbox. We know the bench will not fail. Okay? And last, after experiment, we compare the experimental results in terms of displacement. We compare with the experiments and the simulation. And we also validate by checking the strain and the failure criteria in the model. So we check everything, in fact, in the model. So conclusion, the simulation has been used to design and optimize the complex structure. We use the simulation to design the bench, to validate the bench. And now we know we can use simulation to reduce the number of tests. So if you have a complex part to test, we can simulate first to save time. So finally, simulation save time and money for the industry, as we show. So thank you very much.